Okay, here's some problems from section 1.5 that deal with some functions, combination of functions, and some of these are so straightforward combinations that it's almost insulting to you. You're going to see how difficult some of these are. Like, here's what we can do. We can add functions together. We can multiply functions together. We can subtract functions, and we can divide functions. And the only tricky part here might be finding the domain. To add functions together, we've got options here. We can say that a f plus g of x can be treated as f of x plus g of x. Or we could pre-combine f plus g. I could add this and this together and then go ahead and simplify. For instance, if I was putting a 3 in there. But either way, this is it. F plus g of x is f of x squared minus 4 plus x squared on x squared plus 1. All right, let's take a breath. That was pretty hard before we go on to part B. You're going to ask, is that it? Well, you could simplify this. You could get common denominators on this guy and combine it, but it's still going to be pretty much a mess. So I think that's probably as good a stopping point as any. So, but we all know that subtraction is harder than addition. We don't learn to subtract until much later than we learn to add. So here's subtraction. F minus g of x is f of x square root x squared minus 4. Here's the hard part, minus x squared on x squared plus 1. So we can see subtraction just a lot harder. And then it isn't until like years later that we talk about multiplication. Well, multiplication must be pretty hard. So here is multiplication. C fg of x, or f times g of x, is the product of the two. So that would be root x squared minus 4 times x squared all on x squared plus 1. So yeah, that's much, much harder. Of course it's not. Very, very simple. Now, granted, this is problems that's just not going to simplify out nicely. If there was some simplifying that would look reasonably easy, we would go ahead and do that. And f on g of x. So here is part D. F on g would be f of x root x squared minus 4 on g of x, which is x squared on x squared plus 1. And that one I would expect we would simplify that guy. We're going to go ahead and simplify that guy into x squared plus 1 times root x squared minus 4 all on x squared. And now we have to ask ourselves this last one. What is the domain of f on g? Well, I can start taking this thing apart. I cannot risk g being 0. So what makes g become 0? The only thing that makes g become 0 would be if the numerator is 0. But let's look at, let's start with that. So x, if you look right here, x squared cannot be 0. So far we know x cannot be 0. What else might give us some problems in this guy? I do note there's nothing that's going to make x squared plus 1 be 0 except for imaginary numbers. But I do know that x squared minus 4 better be greater than or equal to 0. That means that x better be greater than or equal to 2, or x better be less than or equal to negative 2. So on a number line, I'm going to squeeze it in down here. Here's numbers that are good. We can be 2 or bigger. We can be negative 2 or smaller. We noted earlier we can't be 0, but 0 is already included. So how's that for domain? So the domain can be the tricky part, and as I've said a number of times in chapter 1, domain probably one of the biggest challenges we have on the test. So we would expect some questions regarding that. Okay, evaluate f of, well, we've been doing this stuff before. It's just now we're combining functions. So again, what I could do is I could find f of 3 plus g of 3, or I could find f plus g of x and combine these guys together first and then put 3 in. But I'm just going to find f of 3 plus g of 3. So that would be 3 squared minus 1 plus 3 minus 2, or 9, 8 plus 1, 9. That easy. So f g of 3t squared. I could find f times g of x, FOIL these out, multiply these against each other, and then put 3t squared in. But I think I'm just going to put 3t squared into f, 3t squared into g, multiply the results. So I get 3t squared squared minus 1 times 3t squared minus 2, or 9t squared minus 1 times 3, 9t to the fourth, excuse me. I heard you out there. I heard you. 9t to the fourth minus 1 minus 3t squared minus 2. Let's FOIL that. I get 27t to the sixth minus 18t to the fourths minus 3t squareds plus 2. And this is where simplified is in the eye of the beholder. Is this simplified, factored form, or is it simplified after we get this unsimplifiable mess? You take your pick there. I can live with both. We should be able to get from one to the other. Okay, this is the combination of functions that I find kind of interesting. And some people will call this fog and Goff. This is really f of g of x. And I really like, this speaks to me because this says I'm going to take x, I'm going to put it into g, I'm going to get g of x, I'm going to put that guy into a factory called f, and I'm going to see what I end up with. So I'll clear off some space for parts B and C, but that speaks to me. So I'm going to find f of g of x is explicitly x cubed plus 1. And f is a factory that takes things, puts them right here, so this becomes the third root of x cubed plus 1 minus 1, which is just the third root of x to the third, which is just x. Huh. So after all this stuff happens, we just end up with plain old x. Okay, so that is part A. Part B, we are looking for g of f of x, which of course just means that we're going to go into f first, get an f of x value, and then place that into g. Or we're going to take g of f of x. F of x is explicitly third root x minus 1. And g is a factory that takes things, cubes them. Oh, let me come back to that. I'm getting ahead of myself. Okay, so now g of that thing, g is a factory that takes things, third root, x minus 1, cubes them, and then adds 1. But that is third root of this to the third just becomes x minus 1 plus 1, or x. And right now you are thinking, I hope, we always look for patterns. That's where we go from being mathematician to scientist. You're saying, f of g of x ended up being the same thing as g of f of x. I wonder, much like 7 plus 3 is the same as 3 plus 7, is the composition of functions, what is the word? So many people get this wrong, this word wrong. They know what it is, but they say Commutative, like community, from a commune. It's commutative from the root word commute, which means home to school is the same distance as school to home. Home to school, school to home. You're commuting. You're wondering, is this commutative? And the answer to that's going to be revealed pretty soon, I believe. But let's hold on to that thought for a minute. Okay, C, f of g of 0. Now, I could go through the process of putting 0 into f and see what I get, and putting the result of that into g and see what I've got. But I have built my f of g, or my f of g of 0. I've built an f of g of x factory, and it says what I end up with is what I started with. So I start with 0, it turns it into something, but f of g of x, this is f of g of x right here, is a factory that just makes x's. So if I put 0 in, it's a factory that's going to take that 0, turn it into 0. Okay? Kind of a unique problem, perhaps. Let's take a look. So we're going to kind of investigate. Here's your vocabulary word. We're going to get it right today. Commutative, from the root word commute. Okay, same problem. So I don't have to draw the picture again. We know that A, we are looking for f of g of x. That notation speaks to me more than Fogg and Goff. That means I want to take f of g of x is explicitly 5 minus x. And f is a factory that puts things right here. So we get 3 times 5 minus x plus 5, or 15 minus 3x plus 5, or negative 3x plus 20. Okay, so now here's our big commutative test. B, g of f of x. If this is commutative, then we might start building up some data that makes us think this is a rule. So g of f is 3x plus 5. G is a factory that puts things right there. Careful, we need the parentheses around this binomial. So g of x is equal to 5 minus 3x plus 5, and I get negative 3x. So far, so good. But I get 5 minus 5, 0, just negative 3x. So we now can determine that if I've done this right, that the composition of functions is not, in fact, commutative. And here is f of g of 0. F of g of 0. But I've built an f of g factory. I expect it to be negative 3 times 0 plus 20, 0 plus 20, 20. But let's go through the process on this one. So this is f of g of 0 would be 5 minus 0. F of 5. F of 5 is 3 times the thing, 5, plus 5, or 20, just as if I would put 0 into my factory, negative 3x plus 20. Overall simple. It's just kind of a different way of looking at anything. So I really, really want to emphasize, I prefer this because it's visual to me. I can see putting something into G, and then the result of that comes out, goes into factory F. What do I get? Fogg, Goff, not my favorite notation. The book uses it, and you should be familiar with it, but perhaps if you're like me or visual, you might want to write things in this form. What a mess. Okay, determine the domains of f, g, and f of g. Again, Fogg, f of g of x. All right, we want to determine the domains of f. Well, when I look at f, no problem with the 3 in the numerator. I can square any number I want. I can subtract 1 from any number I want, but I cannot divide by 0. So x squared, this is a, x squared minus 1 cannot equal 0. X squared cannot equal 1. X cannot equal plus or minus 1. Let's go B. G of x. Don't need that there. We can see it's g of x. So x plus 1. I can take any number I want and add 1 to it. So it is all reals. There's a good abbreviation for all reals, kind of like the paragraph symbol. All reals, though. F of g. F of g of x. So B, I think I'm going to find f of g of x. So here is f of g of x. That is f of x plus 1. That is 3 on, f is a factory that puts things here, x plus 1 squared, and then subtracts 1 in the denominator. So this is 3 on FOIL, x squared, plus an x, plus an x, plus 2x. I'm going to get a plus 1 here when I take 1 times 1, but I've got a minus 1, so I'm going to stop there. That is f of g of x. Well, I can square any numbers I want. I can multiply any numbers I want by 2, but I can add any numbers I want, but I cannot divide by 0. So x squared plus 2x cannot equal 0. X times x plus 2 cannot equal 0. X had better not be 0 or negative 2, or else we risk breaking the machine. Notice, you may say, well, what about, since we're using f of x, what about x squared minus 1? Then x couldn't be 1 or negative 1. But when I put 1 into g first, it changes it. So at the very beginning here, we might have said, wait a minute, f, x squared minus 1 can't be 0. X can't be plus or minus 1. Compare that to this. And the answer is revealed. Negative 1 would be bad. What's going to give us negative 1? Okay, give some thought to that one. Find two functions. This is beautiful. This is Keebler's Elf Cookie Factory ready to go on strike. We got a function. My Keebler's elves are doing this, and production is great, and the demand for this product is awesome, and they got to make more and more and more. And these elves are like, take a look at what we're doing. We're doing so much work here. We have to take things, multiply them by 2, add 1 to them. We still have to square them, and they want us to get all this done in this tiny little tree. We have to expand. We need another tree. We've been doing all of this stuff in a tree called H. But now I want to have f of g of x, fog x. I want to be able to take x, put it into a tree called G, open up a new tree, hire some more elves, call that tree F, and let F do the rest of the work. So here's the important part of this. G has to do the beginning work. And the work would be order of operations. I start with something, I multiply it by 2, I add 1, and I square it. We basically have 3 steps here, and now the elves have to debate. Do we want G to multiply by 2, or do we want G to multiply by 2 and add 1, and leave the rest to H? Let's let G take care of the first 2 steps. If G of x takes the x, multiplies it by 2, adds the 1, what is left for x to do with the thing it delivers? It just has to take the thing that's delivered to it and square it. You can see if I drop x into g, we get 2x plus 1. Then drop that into f, we get quantity 2x plus 1 squared. As an option, we could have said g of x. After a while, let's say this happens with our elves. They meet at a picnic, and these elves and these elves sit down at a table. They don't see each other very often. So here's a table. They're sitting across from each other, and the elves at Factory G say, "Hey, what do you guys do during the day?" And the elves at Factory F say, "Well, we square things." And the G says, well, that's pretty cool. And then they start thinking, they say, wait a minute, they just square things. We have to take things and do 2 steps. That's it. We've had it. For the next year, you guys have to do steps. So G says, we'll do this. We will take things and double them. What does F have to do then with the thing delivered? It has to add 1 to the thing, and it has to square the thing. So either of those would be viable options. And hope that helps. I will have another video on 1.5 involving some graphs for you to take a look at, but that should get you started.